Well, today we're getting our introduction to the unit circle. Our objectives include special right triangles in a circle and the unit circle, but that second one we'll actually do in class together. So we start with the special right triangles in a unit circle, and a recall. Triangles are similar if their corresponding angles are equal and their corresponding sides are proportional. All right, so we did a lot in the last section building up those special right triangles, and we did a few problems towards the end with a angle intersecting a circle somewhere. So we can work with that here. We can think of this for number one, determine the values of the 6 trig functions for an angle of pi over 6 radians in a circle with radius r. And we can think over here that it's going through some point x comma y. All right, and so our x value is that distance out from the origin to the left or right, in this case to the right, into quadrant 1 over here, if we think of being centered at the origin. And our y distance is up from that origin. So we've got x, y, and r, the radius of the circle, with an angle of pi over 6 radians. And that pi over 6, just to do a little scratch to take you back, we might remember is the same as 30 degrees. So really, we're working with a special right triangle, just written in radians there. But we'd have 30 degrees down here and the reference angle, the 90-degree angle, and that leaves 60 for the third angle. In radians, that'd be a pi over 3 up there, and then pi over 2 for the 90. So we've still got a 30, 60, 90 triangle, and those ratios we built up in the last section will apply here. If our radius or our hypotenuse is r, then our opposite side, right, opposite that reference angle, is the short side here because it's opposite that smallest angle, is going to be that r over 2. And our adjacent side, the long side here, opposite the 60, is going to be root 3 times that value. So we get an r root 3 over 2. All right, and so we can use those opposite, adjacent, and hypotenuse, the sides of this triangle we've got in the quadrant 1 here of the circle, to get the values of our trig functions. For sine of pi over 6 then, we get our opposite over hypotenuse, or our r over 2 divided by r as a fraction, r over 1. So our fraction division gives us an r over 2 times 1 over r. Those r's will divide out, right? Common factor in the numerator and denominator, leaving me with a 1/2 for sine of pi over 6. And its reciprocal then, cosecant of pi over 6 would just be 2 over 1. For cosine of pi over 6, we're working with our adjacent over hypotenuse. Our adjacent was the r root 3 over 2 divided by our hypotenuse r, or r over 1 to view that fraction again. With our fraction division would give us r root 3 over 2 times 1 over r. Again, the r's divide out, and we're left with a root 3 over 2, which makes our secant of pi over 6, 2 over root 3. And for tangent pi over 6, we've got opposite over adjacent for a r over 2 divided by r root 3 over 2, which gives us r over 2 times 2 over r root 3. We can see those r's still divide out, and now the 2's divide out as well, leaving us with just a 1 over square root of 3. And the reciprocal then for cotangent pi over 6 would become just the square root of 3. So if you do look back in your notes, or you might just remember, those should be the same values we got for that special right triangle for the 30, 60, 90, really for the 30-degree angle. The same ones we built up a couple times in the last section. So the point here, doing kind of the same thing again, is that the side lengths here don't affect the ratios. So we'll use a unit circle to further our understanding of the trig functions. A unit circle is a circle with radius r equals 1, and center at the origin, which we all remember now is 0, 0, of the Cartesian plane. The equation for the circle is x squared plus y squared equals 1. And we'll do some more work with circles later in the course. Fun fact, we know that the circumference of a circle is c equals 2 pi r. So the unit circle has a circumference of length 2 pi, right? If r is equal to 1, we just get 2 pi there. And again, we see the connection between radian measure and arc length. In a unit circle, the central angle is the same as the arc length. And if you look back, that was how we introduced what a radian was, right? It was an arc that had the same length as a radian. So really, in this unit circle, the angle that we open is going to be equivalent to a distance or an arc we trace along the circle, which is really just important for working with real-world values and problems and things. So really, we're just talking about distances when we talk about an angle in the unit circle. So a note here to finish the first page, if we trace an arc in the counterclockwise direction for any positive value, and in the clockwise direction for any negative value, we can map any real value to a point on the circle. So that should match with our definitions for the positive and negative motions or directions for the angles as well. All right, so what we're leading up to. Definition. Let theta be an angle whose terminal side passes through the point P equals xy that lies on a circle of radius r. So then we have these sides labeled kind of the way we did above. We'd have this point xy if we want it. And we're going through the origin, if it helps you, 0, 0. But then the opposite over hypotenuse we had for sine theta becomes a y over r. Our cosine was adjacent over hypotenuse. This is going to become x over r. And our tangent that was opposite over adjacent is going to become y over x. So the reciprocals then, cosecant theta would be r over y, secant theta would be r over x, and cotangent theta would be x over y. But note here, we're on the unit circle, so r equals 1. We get the following definitions that we're going to use. Sine of theta is just y, because all those r's would become a 1. Cosine theta is just x. Tan theta is still y over x. Cosecant theta becomes a 1 over y. Secant theta becomes a 1 over x. And cotangent theta is still x over y. All right, a note here that we'll talk a lot more about in the future. With these new definitions, we get an important result in trigonometry, and we'll touch on more later. X squared plus y squared equals 1 becomes, if x was cosine theta, we get a cosine squared theta plus y is sine theta there. Sine squared theta equals 1. This is a Pythagorean identity. It's going to be really important when we work with the identities for trig. But for now, we'll do a couple little problems to talk about the quadrants really of the circle, and then build more together in class. So for 2, we want to find the value of tan pi over 3. So we can draw a special right triangle with pi over 3 as our reference angle. 90 degree, which makes this pi over 6, or really our 30, 60, 90 again. Since the side lengths don't matter, or that value for r didn't matter, we're using our unit circle, so 1 for our hypotenuse, right across from that 90, which makes the short side half of that. So 1/2 down here across from the pi over 6, and the long leg, that root 3 over 2. So for tan pi over 3, we want our y over x, which is going to give us the root 3 over 2 divided by 1/2, or root 3 over 2 times 2 over 1. Those 2's would divide out, and we're left with just a root 3. All right, 3, 4, and 5 are more questions kind of about the quadrants, so we can draw a little circle over here. And you can use probably the same thing for some of the questions on the ticket. It's just getting used to where everything lives. So I'm going to label these 4 points, right? If we're on a unit circle, centered at the origin, radius 1, then out to the right, we're at a point 1, 0, right? 1 to the right, 0 up or down. At the top, we've got a 0, 1, 0 left to right, 1 up, -1, 0 out to the left, and 0, -1 at the bottom. We also know we've got 0 radians, pi over 2 at the top, pi on the left, 3 pi over 2 down at the bottom. But we come back around to 2 pi there. So, for what values of theta does sine theta equal 0 on the unit circle? For sine theta to be 0, we want the y value to be 0, right? We know sine of theta was equal to y, so where is our y value 0? That's going to happen at 0, pi, and 2 pi. Right? We can see all those 0 values for the y. And if you did want to keep going around the unit circle in either direction, we could kind of keep going with this, right? 3 pi, 4 pi, 5 pi, 6 pi, or even backwards, minus pi, minus 2 pi. And we'll see that when we work with the graphs later on. In what quadrants would tan theta be less than 0? So we had our quadrant 1 over here where we had positive x, positive y. Quadrant 2 where we had negative x, positive y. Quadrant 3, negative x, negative y. And quadrant 4, positive x, negative y. So for tan theta, which is equal to y over x, to be less than 0, we just want a negative value. So we'll get a negative value when our signs are opposite. So that's going to happen in quadrants 2 and 4. Right, in quadrant 1, where both are positive, we'll get a positive ratio. In quadrant 3, when both are negative, those negatives will divide out and give us a positive ratio again. 5, where on the unit circle would the value of secant theta be undefined? So secant theta, I'll use the reciprocal, is the same as 1 over cosine theta. This is undefined if we're dividing by 0. So if cosine theta equals 0. So we talked about where sine was 0, all the places where we're on the x-axis, right, where we have no y movement up and down. If cosine theta equals x, then we're worried about where theta equals pi over 2 and 3 pi over 2. Those places where x would be 0. And again, we could keep going around the unit circle, 5 pi over 2, 7 pi over 2, or backwards, minus pi over 2, minus 3 pi over 2. But we'll talk about those more as we do more in the future. So note here, every point on a circle can be represented by a right triangle. We can use the special right triangles to map out some common values. As the radius, hypotenuse, or side length do not affect the ratio of the sides, we use a circle with radius 1 to build the circle. And we'll do that together in class. So that's it for now. Take a look at the ticket, and I'll see you in class.